Right, guys. So far we didn't do an example of Frobenius theorem. Remember, Frobenius theorem tells you that if x equal, let's say, 0 is a regular singular point, then to y double prime plus p of x, y prime plus q of x, y equals 0, then there exists a solution of the form y equal x power r summation from n equals 0 to infinity cn x power n, where r solves the initial equation r minus 1 plus p0 r plus q0 equal to 0, where p0 is the limit as x goes to 0 of x px, and q0 is the limit as x goes to 0 of x squared q of x. Now here I told you this is an initial equation. I'm looking for real solution, and there are the following cases. This is the good case, okay, which is I have r1 larger than r2, real solution r1 real solution with r1 minus r2 not in z. Then I have y1, which is x power r1 summation from n equals 0 to infinity cn x power n. This is the first Frobenius solution. And y2 is x power r2 summation from n equals 0 to infinity dn x power n. So I have one solution for each index. The ugly case is when r1 larger than r2, but r1 minus r2 is in z. Then the larger index gives me always a Frobenius solution. But I don't know about the smaller index. It will give me a solution of the form cy1 log x plus x power r2 summation from n equals 0 to infinity dn x power n. Okay. So where c can be 0. If it's 0, then I'm back to the case 1, to the good case. If it's not 0, then I will have a log x that appear. And this is a bad case, is when r1 equal r2. And then in this case, I have y1 equal x power r1 summation from n equals 0 to infinity cn x power n. And then y2, I will definitely have a log x in this case, plus x power r1 summation from n equals 0 to infinity d sub n x power n. Let's do 3 examples. So example 1. Well, the question is always the following. Show that x equals 0 is a regular singular point and use Frobenius method at x equals 0 to solve the ODE. Okay, first equation. Now this example gonna need some time. You have to be very careful when you solve them. 2xy second plus 1 plus x y prime plus y is equal to 0, and this is for x positive. So why is x equals 0 is a regular singular point? So what is p of x in this case? It's 1 plus x over 2x. What is q of x is 1 over 2x. So notice that p is not analytic at x equals 0. This implies x equals 0 is a singular point. And next, I want to show that it's a good kind of bad points. So what is x p of x? This is 1 plus x over 2. This is analytic at x equals 0. What's x squared q of x? This is x over 2. And this is analytic at x equal to 0, and therefore x equals 0 is a regular singular point. Then by Frobenius method, there exists a solution of the form y equal x power r summation from n equals 0 to infinity of Cn x power n. Okay. Now you don't need to find r from the very beginning. Here you need to find r, you need to find Cn. The thing is, you can do these two together. You can find the initial equation while solving. But if you are only interested in what is r, you can calculate r directly, because I know that r solves what? r minus 1 plus p0r plus q0 equals 0, where p0 is the limit as x goes to 0 xp of x, which is half, and q0 is the limit as x goes to 0 of x squared q of x. So this is scratch. If the question was just to find indices, which is equal to x over which is equal to 0, to the limit of this, then the initial equation is r minus 1 plus 2r equal to 0. So this is r minus 1 plus half r. So this is r times r minus half equal to 0. So you have r equal 1 and r equal half. So I'm looking in the good case, because the difference r equals 0 and r equal half. So I look in the good case, yes, because the difference is not an integer. But anyway, let's solve it, and I will show you how we will re-get this equation while solving it. Well, if you solve correctly. Now remember, I have the equation 2xy second plus 1 plus x y prime plus y equal to 0, and I have y is x is summation from n equals 0 to infinity Cn x power n plus r, which I write it as x power r summation from n equals 0 to infinity Cn x power n. What about y prime? So this is summation from n equals 0 to infinity n plus r c sub n x power n plus r minus 1. And I can write this as x power r summation from n equals 0 to infinity c sub n x power n plus r c sub n x power n minus 1. What about y second? This is summation from n equals 0 to infinity n plus r. So if you are used to shift indices, in this case it would be wrong. You don't know if you shift in the... it's not when you differentiate it should start from 1. It's wrong in this case, for example. So this is why I told you not to get used to this habit, to shift the index whenever you differentiate. Cn x power n plus r minus 2, and this equal x power r summation from n equals 0 to infinity n plus r minus 1 c sub n x power n minus 2. Now replace in the ODE. What do you get? Notice that I have x power r, x power r, x power r, so I put 0 equal x power r times 2xy second, so multiply this by 2x, so you get 2 summation from n equals 0 to infinity n plus r minus 1 c sub n x power n minus 1, because I multiply by x. Now multiply 1 plus x by y prime and expand, so it's 1 times y prime plus x times y prime. So this is plus, first 1 times y prime, which is n equals 0 to infinity. Remember, I have x power r outside. Cn xn, this is here. Again, so you have to bear with me that I don't do any calculation mistake that might cost a lot. So this is n plus r Cn x power n minus 1 plus x times this. So this is summation from n equals 0 to infinity n plus r Cn x power n, because I multiply by x, plus summation from n equals 0 to infinity of Cn x power n. And this is my ODE. Now x is different than 0, so I can simplify this. X is positive. Now I solve the same way I used to solve in the case of ordinary point. So I re-index so that all the power are x power k. So I take k to be n minus 1 here. I take k to be n minus 1 here. K to be n and k to be n. Then I get 0 equal to summation n equals 0, then k is, if n equals 0, k is minus 1 to infinity. N plus r, n is k plus 1, so this is k plus 1 plus r times n plus r minus 1, this is k plus r. Cn is ck plus 1 x power k plus summation n equals 0 to infinity, n is 0, so k equal minus 1 to infinity, n is k plus 1 plus r, c sub n is c sub k plus 1 x power k, plus, I didn't change the last two, sorry, it just decided to leave, so this is ck plus 1 x power k we said, plus summation from k equals 0 to infinity, k plus r ck x power k, plus summation from k equals 0 to infinity, ck x power k. Next, I find the largest starting index, which in this case is k equal to 0. And I start expanding the sum till I reach k equal to 0. So the first one is summation from minus 1 to infinity, which is the index, which is the term for index minus 1, plus summation from 0 to infinity. So when k equal minus 1, you get 2 times. K equal minus 1, you get r minus 1, c sub 0, x power minus 1, plus 2 summation from k equals 0 to infinity, k plus 1 plus r, k plus r, ck plus 1, x power k. And this is the first sum. Plus, what about the following sum? K equal minus 1, mean you get r, c0, x power minus 1, plus summation from k equals 0 to infinity, k plus 1 plus r, ck plus 1, x power k, plus summation from k equals 0 to infinity, k plus r, ck x power k, plus summation from k equals 0 to infinity, ck x power k. And now I group all the term outside the sum. Let's see here. You have x minus 1, x minus 1. So this will be 2r, r minus 1, plus r times c0 x power minus 1, plus all the summation from 0 to infinity, k equals 0 to infinity. Let's see what's multiplied by ck plus 1. You have k plus 1 plus r into this plus this. So this is 2k plus 2r plus 1. I took k plus 1 plus r common factor here and here, times ck plus 1, plus, what about the multiply by ck? It's k plus r plus 1 ck, and everything is multiplied by x power k. Okay. Now notice that the coefficient of C0 is what I expected to be the initial equation. You see r minus 1 plus r over 2 equals 0. This is nothing but 2r, r minus 1 plus r. So always you get the initial equation as the coefficient of C0. So as I told you, it will show up anyway in the equation. Okay. So the initial, so I will call this star, and you have to remember. Initial, I mean, you will not remember by heart all this, but you have to go back to it during solving. So initial equation is 2r, r minus 1 plus r equals 0, which is r times 2r minus 1 equals 0. So I have two solutions, which are 0 and half. What is the largest one? So r1 equal half, r2 equals 0, So R1 minus R2 is not an integer, so I'm in the good case. Which means R1 will give me a solution and R2 will give me another solution. So I solve for R1 equal to half. And then I replace, I will get y equal x power half, summation from n equals 0 to infinity cn x power n, replace, and you get this equation. We get star with r equal to half, which means I get 0 equal, r equal to half will make this vanish. So equals summation from k equals 0 to infinity. Now take r equal to half, you get k plus 3 half. Take r equal to half here, you get 2k plus 2. ck plus 1 plus k plus 3 half ck x power k. So I get k plus 3 half, 2k plus 2, ck plus 1. Sorry again, the iPad is crashing. K plus 3 half, 2k plus 2, ck plus 1, plus k plus 3 half, ck equal to 0. Because I have a power c is equal to 0, means the coefficient are equal to 0, and this means ck plus, where this is for k equals 0, 1, 2, blah blah blah, so this is never 0. So ck plus 1 is equal minus ck over 2 times k plus 1. Okay. For k equals 0, 1, 2, this. And this is a recursive relation for k equal, for r equal to half. And now I start plugging in. So k equal to 0, you get c sub 1 is equal minus c sub 0 over 2 times 1. Okay. What about when k equal to 1, you get c sub 2 equal minus c sub 1 over 2 times 3, which is equal c sub 0 over, well, I can write it as 2 times 2 times 3, okay? And you will notice, I will tell you the pattern, but if you couldn't find it, then it's fine, okay? You don't have to worry, but I will solve it in a way to show you what pattern we get. So k equal 1, so this is 2 times 2 here. Okay, so this is 2 times 2 times 2. So this will be 2 squared times 2 factorial. And this, I can notice that this is minus c0 over 2 power 1 times 1 factorial. What is k equal to 2? This is c3 equal minus c sub 2 over 2. Well, you replace 2 times k plus 1 times 3, which is c0 over 2 cube times 2 factorial times 3, which is c0 minus c0 over 2 cube times 3 factorial. Okay, and then for k equal 3, you get c4 equal minus c3 over 2 times 4, which is equal c0 over 2 cube times 3 factorial times 2 times 4, which is c0 over 2 power 4 times 4 factorial. So if you notice the pattern, this will be good. So ck is equal minus 1 power k c0. So ck is equal minus 1 power k c0 over 2 power k times k factorial. If you don't notice the pattern, then it's fine. So y1 is x power half c0 plus c1x plus c2x squared plus c3x cubed plus. So y1 equal x power half times c0. c1 is minus c0 over 2x plus c0 over 2 times 2 factorial x squared, 2 squared times 2 factorial x squared, minus I hope it will not keep crashing. Minus C0 over 2 squared times 3 factorial x cubed plus plus plus. So take C0 outside, so y1 equals C0 x power half times 1 minus x over 2 plus x squared over 2 times 2 factorial minus x cubed over 2 squared times 3 factorial plus plus plus. Okay, and this you can write it choosing C0 to be whatever 1. You get y1 equal x power half 1 minus x over 2 plus x squared over 2 times 2 factorial plus x minus x cubed over 2 squared times 3 factorial plus plus plus. And if you found the pattern, it would be good. Sometimes you will need to find the pattern, and I will tell you find the pattern because it will be the pattern of a function you know. And we will see this at the last example. And now this will be minus 1 power k times x power k minus 1 power k times x power k over 2 power k times 2 times k factorial. Okay, which is not a power series that you know. So this is fine right now. Now how do I find y2? I plug in. Now I take r to be 0. Okay, so I solve, and let's write as I did, solve for r equals 0. So you will have y equal x power 0 summation from n equals 0 to infinity cn x power n, which is summation from n equals 0 to infinity cn x power n. So plugging r equals 0 in star, so I know that this will vanish because this is a, so now you plug in r equal to 0. Try to fix this in the next video. I plug in r equal to 0 here, and then you get k plus 1, 2k plus 1, k plus 1. So you get k plus 1, 2k plus 1, c sub k plus 1, plus k plus 1, c sub k equals 0, and this is for k equals 0, 1, 2, blah, blah, blah. So ck plus 1 equal minus c sub k over 2k plus 1 for k equals 0, 1, 2, blah, blah, blah. And then this is my initial equation. I start k equal 1. I start k equal 1, and I get c sub 2, k equals 0, sorry. C sub 1 equal minus c sub 0 over 1. K equal 1, you get c sub 2 is equal minus c sub 1 over 3, which is equal c sub 0 over 1 times 3. K equal 2 equals c sub 3 equal minus c sub 2 equal minus c sub 2 over 5, which is equal minus c sub 0 over 1 times 3 times 5. And I think here the pattern is easy. C sub 4 is equal minus c sub 3 over 7, which is equal c sub 0 over 1 times 3 times 5 times 7. So if you found the pattern, it's good to write it. I mean, c sub k equal minus 1 power k c sub k equal minus 1 power k c sub 0 over 1 times 2 blah 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 times 2k minus 1. Okay, this is your pattern, and then you will get y2 equal c0. y2 is x power 0, which is x power 1. y2 x power 0, which is 1. Y equal c0 plus c1x plus c2 x squared plus c3 x cubed plus plus plus. But my c0 is 1, so this will be times x power 0. So this will be c0 plus c sub 1, which is minus c0 x, plus c sub 2, which is plus c0 over 1 times 3 x squared, plus c sub 0 over 1 times 3x squared minus c sub 0 over 1 times 3 times 5x cubed plus plus plus. So choosing, so y equals c sub 0 into 1 minus x plus x squared over 1 times 3 minus x cubed over 1 times 3 times 5 plus plus plus. So choosing c0 to be 1, you get y sub 2 is equal y sub 2 is equal, so I choose c0 to be 1 equal 1 minus x plus x squared over 1 times 3 minus x cubed over 1 times 3 times 5 plus plus plus. And this is my second solution. And notice that y1 and y2 are linearly independent. Why is that? Because you don't multiply something that have x power half and you get something that doesn't have x power half by multiplying by a constant. So the solution, is y equals c sub 1 y1 of x plus c sub 2 y2 of x. So y equals c sub 1 x power half times 1 minus x over 2 plus x squared over 2 squared 2 plus minus x cubed over 2 cubed 3 factorial plus plus plus. Oh my god. Y equal c1 y1 plus c2 y2. I apologize for this, I'm not sure why this is happening today. So it's c1 x power half times 1 minus x over 2 plus x squared over 2 squared 2 factorial minus x cubed over 2 cubed 3 factorial plus 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 c sub 2 times 1 minus x plus x squared over 1 times 3. Please. Okay, anyway, I will stop writing this. So it's c1 y1 plus c2 y2, and then this is my y1 and this is my y sub 2. Okay, so I'll stop here. I'll try to fix the video and I will start with the second example in the second video.